రెండు గ్రూపులు పెట్టారా ఇంకో గ్రూప్?
ఎట్లా మనకి అసలు సంబంధం లేదు, చూసుకుంటాం.
ఓకే.
అది మీరు జాయిన్ అవ్వండి.
My short-term goal at present will be to clear the GATE examination and get recruited into any top IITs.
At present, my dream is I want to place in a multinational company.
So I want to be an automobile designer. I want to be in Audi working for Kotaro or Lamborghini.
I like Ronaldo. He's very aggressive. I just want to be like him. That zeal should continue in my life.
GMR Institute of Technology is a premier technical institute located in Rajam in Andhra Pradesh. The idyllic campus offers a good learning environment far from the distractions of the city.
GMRIT was set up almost 17 years ago with the main purpose of serving a very relatively backward region in the country, and the idea was to give a hope and a future for children who otherwise weren't having access to good engineering and technological education.
GMRIT was set up in 1997 by the GMR Varalakshmi Foundation, the CSR arm of the GMR Group.
The idea at the time also was that we will create an institution where ethics, excellence and excitement would be the real work culture, and that we would make some impact in the society with a degree of innovation built into entire curriculum of the institution.
GMRIT offers undergraduate and postgraduate programs in technical education. The courses are rigorous and intense, laying a strong foundation of engineering concepts.
The faculty here, they're knowledgeable and very human, simple, participative, and I think all of that adds a certain value that's so required in society today.
At GMRIT, the faculty is provided with a wide range of resources and customized teaching aids to make the courses more relevant, dynamic, interactive and learner-friendly.
GMRIT is an enabling campus wherein we offer BTech programs in various disciplines. With the group's presence in the airport, we have collaborations with the various industries in India and even universities abroad. To name a few, we had collaborations with almost all the IT giants in India like IBM, Microsoft, Infosys, TCS, and so forth.
GMRIT is giving me lot many facilities. One of the greatest facility which my college is providing for us is IBM, the International Business Machine. We have to move around of understanding with IBM, through which they provide the training on different products to both students and also to the faculty even.
GMRIT provides a technology-enabled teaching and learning environment. The institute provides a platform where students have access to the latest software and technological developments. With the GMR Group being the parent company, emphasis is given to collaborative learning between industry and academia. Students are given practical experience relevant to industry needs.
So I'm doing my PhD in data mining. For doing PhD, I have to refer a lot of journals and conference papers. For doing that, I can use this digital library where the latest publications I can easily access. And while doing PhD, a lot of support is given from this institute, like generous cash incentives if you publish in international journal or national journals. I stay within the campus, so staff quarters are provided. It's a clean environment and it is a pollution-free environment.
GMRIT provides residential and hostel accommodation to all students, faculty and staff. With all amenities located within this green campus, the institute is an ideal place to live and learn.
Football is a very passionate game. I love football. I play every day. Football has taught me many things. It taught me how to be disciplined, how to be responsible. You know, every game is about winning or not about winning or losing. It's about what you gain from your losses. So as in the case of the life.
GMRIT encourages the students to take up a number of extracurricular and co-curricular activities and also work with local communities for their social development. In realizing its vision, GMRIT inculcates in its graduates values of self-confidence, integrity and entrepreneurship so as to bring out the best in them and help them excel in their chosen careers.
At GMRIT, we have multiple campus placements. Like we have a very big companies coming here to recruit students. For getting through interviews, we even get trained at by conducting classroom training programs where we'll learn aptitude, and we'll even have personality development classes. Like they'll tell us how to speak, how to attend the interviews, so that we can have multiple chances through it.
The kind of trainings which are provided to us in GMRIT right from the first year, getting access to the journals.
What's happening in the IT industry today.
The GMRIT, my son has come up as a right student, right citizen. As a parent, we only can give something. Whereas an institution can give the discipline, the character, the basic ethics, the teamwork. All these things will be only given by the institution.
And I think GMRIT contributes to that through education, building engineers, not only building engineers, building citizens. Because we offer soft skills, we offer citizenship skills, life skills.
shaping group of tomorrow.
changing magnetic field. Changing magnetic field also, changing magnetic field can create current, and changing electric field can also create magnetic field. Okay. So if I'm completely true, then why sometimes iron act as a magnet when we touch with a permanent magnet? Let's say I take an iron and then I take a permanent magnet. I keep them together for one night and then I take out. And now this iron, which is not a permanent magnet earlier, is attracting all the other iron things nearby. But you know that I'm not flowing any current, I did not connect to any battery. Okay, there is no current flow that is there. But still, why iron is acting as a magnet? So iron intrinsically is acting as a magnet when you keep them with a, when you keep for some time with a permanent magnet. So there should be some currents that should be there to give you or to induce the magnetism in these materials. So whenever we have a doubt, what we need to do is that we need to go to the atomic structure. And this is our atom. Any material you take, right, it is made of an atom, which more or less, I mean, it is just a schematic, it looks like this. And when we take an atom, do we have any currents? Of course we do have currents. So just like in a solar system, Earth is kind of orbiting around the sun, right? Here electron is orbiting around the nucleus, which means that electron has a charge, which is 1.6 into 10 to the minus 19 coulomb, which is orbiting around the nucleus, which means that there is a flow of charge. So whenever there is a flow of charge, that is a current. So we have orbital current, just similar to sun is orbiting around sun. So this orbital current can give us magnetic field. So we have one source we found. Second one is that just like Earth is spinning around its own axis, so it is revolving around its own axis, electron is also revolving around its own axis. Okay, we can take like this. So when an electron is revolving around its own axis, what is going to happen? We have a second current because there is a charge that is revolving around its own axis. So we have a spin current. So it is not all. Still, there is a nucleus, just like sun, is also revolving around its own axis. So you have a nuclear spin currents. So what I'm saying is that you have three currents in an atom, which we don't feel it. You just take a tiny atom through which all these materials, the whole universe is made. The atom itself has three different currents present in them. One is the electron orbital current, second one is electron spin current, third one is the nuclear spin current. So you have three different origins of magnetism that is present within the atom itself. And how much is that magnetic moment that can be created due to this orbital current in an atom, that is called Bohr magneton, which is 9.27 into 10 to the minus 24 ampere meters. So we get this much of magnetic moment due to one current, that is orbital current, and also similarly you get more or less the same kind of magnetic moment due to the spin current. If you see, for the nuclear spin current, I kind of faded it. The reason being is, you know that nucleus, the mass of the nucleus is 1000 times higher than the electron mass. Okay, so if you see this formula for the magnetic moment, it is EH by 4 pi m. As compared to the electron, nucleus has a mass of 1000 times higher. So when the mass is 1000 times higher, the magnetic moment that is created is going to be 1000 times smaller. Okay, so that's why we can neglect the magnetic moment that is coming from the nucleus. So basically we take the two magnetic moments that are generated. One is due to the orbital motion of the electron, second one is due to the spin motion of the current, the spin motion of the electron. So one is called L, second one is called S. So the people who have done or who have been interested in some physics, right, on quantum mechanics, they might have heard of LS coupling. L is the orbital magnetic moment and S is due to the S is kind of the inducing spin magnetic moment and the coupling. So you have two magnets. Electron, unknowingly it is creating two different magnetic fields. One is due to the orbital motion, second one is due to the spin motion. These two, whenever you bring two magnetic fields or two magnets together, they are going to interact and they are going to couple. Depending on whether it is a north-south or south-north, whatever, whether it is going to attract or repel, but there is going to be some coupling. So similarly, electron itself is creating two magnetic fields. One is the orbital magnetic moment, second one is spin magnetic moment. The coupling is going to be the LS coupling. That is going to tell us that what is the effective magnetic moment that is coming in the magnetic materials. So what I am saying is that every atom, so we are made of atoms, every atom, any material, any element you take, every atom is a tiny magnet. You may ask an immediate question that if every atom is a tiny magnet, why we see this kind of magnetic phenomena or magnetic behavior only in certain materials. So let's look into it. There are different class of magnetic materials we have studied in our +2 itself. And why all materials are not showing similar magnetic phenomena? If at all, every atom is a tiny magnet. Of course, that depends on the electron configuration, that how these electrons are arranged within the atom. Basically, we have several kinds of magnetic phenomena or there within the materials. First one is diamagnetic, paramagnetic, ferromagnetic. Again, in ferromagnetic, you have two subclass. One is antiferromagnetic material, second one is a ferrimagnetic material. Let's quickly see that what are these kind of materials. So basically, diamagnetic materials, if there is no intrinsic magnetic moment. Why there is no intrinsic magnetic moment? If the atom has these tiny magnets, the reason being is that basically diamagnetic materials have completely filled shells. When the shells are completely filled, so let's say one electron is rotating in clockwise direction, second electron is rotating in anti-clockwise direction. That we know that. That is the only difference I see between the kind of earth and electrons. Basically, electron can have two movements. Okay, one can be clockwise, second one can be anti-clockwise. Whereas for air, there is only one chirality. Okay, so when all the shells are filled, one electron is going in clockwise, second electron is going in anti-clockwise. So they compensate each other. Let's say one is giving plus magnetic field, second one is giving negative. It is compensated the magnetic moment, that is zero. So you don't have any intrinsic magnetic moment. Of course, when you apply an external magnetic field, this clockwise is going to maybe, don't take it just like that, but just try to understand that it is going to go with a little bit of high speed, whereas anti-clockwise will go with a little bit of low speed. That can create some magnetic moment that opposes the external magnetic field. Okay, so the reason being is that whenever there is a change in magnetic flux, okay, that will create some EMF. Okay, within this material, that EMF can produce the magnetic field opposing the external magnetic field. This is exactly how diamagnetic materials work. So what I'm saying is that if you bring a diamagnetic material into a magnetic flux, into the presence of a magnetic field, as you can see here, it is going to exert the magnetic flux lines outside. So it is just like kids, when we were kids, right, we try to oppose our parents. Okay, we came from there. So the magnetic field is induced here, but it is going to oppose the magnetic field that is coming from the external. So it is going to expel the magnetic field lines when they are trying to go through this material. So this kind of materials are called diamagnetic materials. So just a simple example is like a child is rebelling against the parents. Of course, we all might have heard about superconductor is a perfect diamagnet, which means that it will expel all the field lines. It would not allow any field line to go through it. Okay, so when it is not allowing any field line to go through it, what is going to do is that it is going to repel the magnetic materials that are coming close to it. So you will have a magnetic levitation. Okay, so if at all, when we get so this is a magnetic levitation which I am showing here. This is a superconductor, and when we put a small magnetic pellet on top of it, you can see that is going to float in the air. Just because that magnetic flux lines of this guy cannot flow through this superconducting material. So what if we get a superconductor that can work at room temperature? We will get maglev trains, where the trains doesn't need to. You just take you make the track as a superconducting, and the train, whatever the wheels, right? You can make it as magnetic. Then what is going to happen is that they are going to flow, just like they are going to fly actually. Okay, so they don't directly go on the track, but they will go a little bit higher than the track. So whenever the train can go a little bit higher than the track, you can go against the friction, so you can achieve speeds that are close to 600 km/h, which is more or less like a flight. Flight can give you a speed of 800 km/h. Okay. So the best part is that you can see that we can travel faster than sound. Okay. Of course, so far there is no room temperature superconductor that is discovered. So second kind of magnetic ordering is coming because of the intrinsic magnetic moment. So just now, as I mentioned that whenever all the shells are filled, let's say one spin is like this, or the other spin is like this, they are going to compensate each other. You will get zero spin. Let's say that there are unpaired electrons in the shell, which means that only one electron is there. Either it is clockwise or anti-clockwise, it is going to give you the effective magnetic moment. That is called the intrinsic magnetic moment. Okay, so whenever this intrinsic magnetic moment is there, each and every atom is going to act as a magnet. Every tiny atom is going to have act as a magnet, which is like a north and south pole. So that is the smallest magnet that we can create, a small atom. And you know that magnetic monopoles doesn't exist. If you break a magnet into small piece, right, you will always get one more magnet with north and south. Okay, so what I believe that the smallest magnet that you can create is an atom. Okay, just like aluminum, if you take an aluminum atom, it is a small magnet. Okay, if at all this is true, why not all materials are behaving like iron, cobalt and nickel? The reason being is that they have a small exchange interaction, that even though these all atoms are magnetic, they are not supporting each other. They don't have any exchange interaction. It is just like they are chaotic. They don't have any friendship. So they want to randomly oriented. So when all of them are randomly oriented, the effective magnetic moment is again going to be 0. So it looks like a diamagnetic material, but it is just because that all these atomic magnetic moments, they are oriented in different direction. You may ask me that why they are oriented in different direction. You all know that in our ambience, right now there is a temperature, let's say currently maybe 25 degrees centigrade. Okay, so whenever there is some temperature around it, you have thermal energy. Okay, that is kBT. At room temperature, you have an energy of 25 milli electron volts. So the exchange interaction, so if the two spins are there, when the energy they are keeping it together is less than 25 milli electron volt, they will just randomly oriented just because of the thermal energy that they are taking from the surroundings. Okay, so what happens if they have good friendship? They have a strong friendship and they want to state and give you the ferromagnetic material, this temperature around it. Of course, conditions apply. It would not happen forever. You just keep on increasing the temperature, let's say to some 600 degrees centigrade. Okay, some 600 Kelvin. We should talk always in SI units. So let's say you increase to some 650, 700 Kelvin. Again, this magnetic material behave like a paramagnetic material only. So when you have a strong exchange interaction, that will give you the ferromagnetic nature, where all the spins are going to stay together. Basically, ferromagnetic materials find several of applications in the magnetic device. In today's lecture, I am going to focus mainly on ferromagnetic materials. What are the magnetic materials we are so far talking, or what are the magnetic materials that we are using in our day-to-day life? Knowingly or unknowingly, we are all using magnetic materials. Okay, so all these magnetic materials are mostly made of ferromagnetic materials. Of course, there are two other types of materials that exist: antiferromagnetic and ferromagnetic. So in antiferromagnetic, there is an exchange interaction between the neighboring spins, but it is opposite to each other. So when they are opposite to each other, the magnetic moment, the effective magnetic moment is going to be 0. In ferromagnetic material, they are oppositely aligned, but only difference is that, as you can see here, their relative magnitude is different. So one of the magnetic moment is higher as compared to the second magnetic moment. So that's why you will still have some effective magnetic moment. And ferromagnetic materials also find some application in our day-to-day life. Okay. So today I will mostly focus on ferromagnetic materials. Of course, you may be wondering that when I'm saying that what kind of applications that we are, I'm talking in day-to-day life. Of course, you all might be sitting under a fan right now. Okay, it is so cold, I did not put fan on, but you might be sitting on a fan here. So that you know that there is a magnet that is converting this electrical energy into the electrical energy into the mechanical energy. Okay, so we all have studied the Fleming left-hand rule. So when there is a magnetic field in this direction and there is a current that is applied in this direction, you will have you will have a mechanical force acting in this direction. So if you can create the mechanical motion by using magnetic fields. Opposite is also true. You know the turbines. So when the turbines are rotating, if you apply a magnetic field, the mechanical energy can be converted into the electrical energy. This is how we are using turbine to generate power. Okay, and also this morning you should have to switch on to bring the water from the groundwater to up, right? So all these things, they all have magnets in there. Okay, so you can see that this motor and stator. Of course, these are the day-to-day things, and we are all using a hard disk. These days, everybody has a hard disk. And you know this hard disk, the memory, the data storage is happening because of the ferromagnetic materials. We are storing the data in hard disk drive due to the ferromagnetic material. And this is a very common to hear about MRI. Somebody got an MRI imaging. Okay, so this MRI, you need strong magnetic fields that will help you to get the MRI scanning. And these days, there are a lot of research is going on to use the magnetic materials for targeted drug delivery. So how does it work? It is just like, let's say there is a cancer tumor in somebody's let's say hand or stomach somewhere, right? If at all we take an external medicine, that is going to kind of give side effects to the whole all over the body. So what they are trying to do is that they want to deliver the drug only to the tumor. So how to do that? So first of all, they coat the drug to the some magnetic nanoparticles and they inject into the body. And using some magnetic fields, because these are magnetic nanoparticles, they can be driven by the magnetic field. So they will drive these magnetic nanoparticles to the tumor. And when they come to the tumor, so they are going to apply some magnetic field. That is alternative magnetic field. So this magnetic nanoparticles are going to vibrate. So when they vibrate, they release this drug to the tumor, and tumor can be tuned. So without any side effects to the rest of the body. So this is called targeted drug delivery. A lot of research is happening to use this magnetic nanostructure for biomedical applications. So if at all time permits, I will discuss a little bit about such kind of things today. So with that brief introduction to magnetic materials and origin of magnetism, I would like to talk about my work, that is spintronics. So spintronics is not a kind of what to say hi-fi word. So spintronics is that how to use these magnetic moments for some electronic applications. So we all have heard of microelectronics, okay, or nanoelectronics. So where we use the charge-based devices. So electron charge is going to go through the transistor. In spintronics, we will use a different property of electron that we will discuss today. So whenever you have a computer should do three things. Okay, whenever we have some data, we need to have three things that has to be done. The first thing is that we should be able to store the data. Let's say you take a photo, you want to store this photo. Okay. You don't like the photo, what you will do? You want to process this photo. You want to give some lighting in the background. Okay. So just like image processing. So whenever you want to process, you need to do some kind of logic. Okay, that can be computation. And once you find that, okay, now the photo, the image is very good, what do you want to do? You want to share with your friends. So you want to WhatsApp or you want to Facebook, you want to send this data. So for that, you need communication. So today in this talk, I'm going to focus on how spintronics can be used for data storage, data processing, and data communication. If at all time permits, I will talk about a little different kind of field, that is how spintronics can be used for medical applications. So usually whenever I give a talk, I always want to have an interactive session that I would ask, I would pose a question, and whenever I get the answer from there, I would go. But today, what I'm going to do is that I will ask a question and I answer myself. Okay, so both are me. I'm the one who is talking, and I'm the one who is also an audience today. So what language computer can understand? We all know that is binary language. So you may speak Telugu, Tamil, Gujarati, Marathi, French, Spanish, English. For computer, doesn't make any difference. You can the computer can be made in China, Russia, US, or India. It will only speak two letters, 1 and 0. Okay. And then who is doing all this processing in our computer? And whenever we buy a computer, the first thing we'll see that what is the microprocessor. So this microprocessor is the heart of any computer. Either you take a phone, computer, laptop, anything, a workstation, or a gaming iPad, anything. They have a microprocessor which is doing all this data processing. But how is it doing this data processing? So this microprocessor has building blocks that are called transistors. So these days there are billions of transistors that are placed in this microprocessor, where this 1 and 0 are represented by presence and absence of charge. So how does this 1 is represented? Whenever, so this is just a simple transistor, field effect transistor. So where you have a source and drain, whenever you apply a gate voltage in such a way that you open the channel within this between source and drain, current can flow from source to drain. So whenever you remove this gate voltage, what is going to happen? The channel is getting closed, so there will be no current flow. So if you see clearly, whenever there is a charge flow through the transistor channel, okay, channel is nothing but the one which is beneath the gate in the semiconductor material, that is represented by 1. Whenever there is no charge flow, that is represented by 0. So today what I am going to talk about is not charge flow, but I will use a different property of the electron. Okay, to do the same thing what we are doing with the charge based devices. And we know that electron has charge, that is a negative charge, that is 1.6 into 10 to the minus 19 coulomb. It can never become positive. But electron has another property, which I have already mentioned, that this is also an intrinsic property, quantum mechanical spin. So electron can rotate in clockwise direction or anti-clockwise direction. So these two things, whenever electron is having an upspin, let's say it is a clockwise direction, that is represented by upspin. When the electron is revolving, kind of spinning in anti-clockwise direction, that can be represented by downspin, which can be assigned to 0. So if you see earlier in charge-based devices, we were using the flow of charge or accumulation of the charge as 1, dissipation of the charge as 0. Now in spintronics, I am using the upspin. So I can just use a single electron. If this electron is electron has a clockwise spin, that is 1. If electron has an anti-clockwise spin, that is represented as 0. So basically spintronics is still using the electron, but a different property of electron. Electron has several intrinsic properties. It has mass, it has charge, it also has a spin. Okay, and we know that electron spin can be plus half or minus half. So using this electron spin or the electron magnetic moment, that is plus half and minus half, today I will show you how we can create data storage, how can we store data as upspin and downspin, and how we can process the data, that is the logic, how to get this NAND gate operation, NOR gate operation, and also I will show you how to get data transfer, how to use this pin for the wireless communications. And you may ask me that when microelectronics already exist and all is set, okay, the process is set and we are all happy with microelectronics, why do we still need to use spintronics? The reason being is that spin property of electron is non-volatile, which means that
Chandrasekhar sir, sorry to interrupt you. Your voice is not able to reach us, sir. Hello, Chandrasekhar sir. Hello, Chandrasekhar sir. Chandrasekhar sir. I think there is some problem. Let me try to solve it. Participants, please stay online. Due to heavy rains in Hyderabad, I think people around AP might be knowing that there is heavy rain in the last night and 2-3 days, since 2-3 days. So there is a lot of disturbance. Sir, we can see you. Chandrasekhar sir. Participants, please stay online. we are experiencing some problems due to weather, bad weather. There are some things which we cannot plan. So please stay online, and we hope the things will get better in some 2 to 3 minutes. All are requested to kindly stay online. Hello, sir. Chandrasekhar, sir. Are you there, sir? We are not able to hear your voice, sir. Voice is breaking, sir. Yeah.
Hello. Yeah, can you hear me? So could you please, yeah, so you please tell me, no, not here. Can you hear me through the... Okay, great, great. So I continue then. Okay. If there is any problem, please call me back. Okay. Okay, thank you, thank you. Okay, so as I mentioned that there are a lot of advantages with this filtronics. That is, if you take a capacitor-based device, too much of rain last night and there was a flood because of the which we are facing a lot of power issues. But I'm trying to use my internet. So please accept my apologies. So for why really need memory? Why we really need data storage? And we know okay, these days we are creating a lot of data. So whenever we see a rain, whenever we see something is beautiful scenery, we take a photo. And only one photo, we take several photos. We just keep on taking photos, and then we don't stop there. The moment we take the photos, we are going to upload somewhere. But when you are uploading somewhere, but right? Someone has to store data. So that can give it to WhatsApp. So they have to store this data. So how they are sharing this data? If at all, we all of us have seen CD disk, right? Compact disk. So if you use a compact disk to store this much of data, okay. So much data that we are taking is 2 quintillion data, 2 quintillion bytes. So if you put that, right, I don't know how many zeros, but this much of data is getting each and every day. Okay. So if you want to store this much of data in CDs, compact disk, then what you can do is that in one day, okay, you just share these CDs, which in one day you can go to them. So you don't okay, so jokes aside, all these companies, right, all these Twitter and stuff, they're storing this data in cloud. Cloud storage doesn't mean that they're storing the data in somewhere clouds. So whenever it's raining, it may come down. No, cloud storage is mean they have some data center somewhere in US, Singapore, or Germany. where they have kept several of hard disk drives. So these hard drives are going to save such of data. You see that you have to create so much of, you have to kind of navigate so many hard disk drives to store this much of data. Okay, so what needs to be done is that how much small area that is using to store one bit, that has to be changed, and that should be as small as possible. If at all possible, it should be few nanometers. So you should be able to store data in nanometers. Then only you can store few terabytes in your hand. Otherwise, if you hello, hello, అసలు రావట్లేదా? ఓకే ఓకే ఓకే, and I'll put PPT again. Okay, I turn off the video. Yes, certainly. I turn off my video. You please stay on line once, so you can see my screen. Perfect. So I'll continue without video. Okay. Thank you. Okay. So just now I mentioned that I can represent data bits, 1 as upstream and 0 as downstream.
Sir, voice is again breaking, sir. Chandrasekhar, sir. Sir, we are not able to hear you, sir.
Yeah, I'm connecting to a different network. I hope now you will be able to hear.
Yeah, now it's okay.
Okay, perfect. Thanks. Yeah. So now I connected to IITH, so I can even turn on my video, not a problem. Okay, so to read the spin state, let's say that when there are two ferromagnetic materials that are parallel to each other, when you measure the resistance across it, the resistance is going to be smaller. The reason being is that when the electrons are flowing from one ferromagnetic material to the other ferromagnetic material, only the one kind of spin, you can see that the spin that is anti-parallel is going to get, that is the only one which is getting scattered. When these two are anti-parallel, as you can see here, both, let's say that majority spin and minority spin, both spins are going to get scattered. So this is why when the two ferromagnetic layers are parallel to each other, resistance is low. When they are anti-parallel to each other, resistance is going to be high. So just by measuring the resistance across this device, we can tell that whether the spin state is in minus x direction or plus x direction. So from there we can tell one is 0, second one is 1. Okay, so this is to read the spin state. Now we need to see how to kind of manipulate the spin state or how to write a spin state. So this kind of device we are already using, this magnetoresistance device we are already using in our hard disk drives as a read sensor. So to manipulate the spin state, the same phenomena can be used where you flow electrons through this device. So these electrons get polarized in the polarizer, and then when they are moving through the second ferromagnetic layer, as you can see here, initially they were anti-parallel to each other. When these spins are flowing through the second ferromagnetic layer, they get they have to change their angular momentum according to the local magnetization. So when they are changing their angular momentum according to the local magnetization, according to Newton's third law, whenever there is a action, there will be a reaction. Now, these spins are going to exert torque on this magnetization that can switch the magnetization, that can switch the free layer. So just by using a small current, you can measure the spin state, and using a large current, you can switch the spin state. So the interesting thing is that you are using the electrical current both to read the spin state and also to manipulate the spin states. I can tell you that we should be thankful to this coming up with this phenomena. For reading the spin state, Albert Fred and Peter Grunberg, they have come up with the idea of giant magnetoresistance, that is the GMR phenomena, for which they got Nobel Prize in 2007. And for predicting the spin transfer torque, which is by applying current, we should be able to manipulate the spin state or magnetization state of a ferromagnetic material. For predicting this phenomena, Luckberger and J.C. Slonjewski, they got Olivier E. Buckley Condensed Matter Physics Prize in 2013. To conduct all the research. You may be thinking that why I am thanking them. You should understand that how much revolution that has created, the kind of phenomena they have created, they have discovered. So this is the first hard disk drive that is made in 1956 by IBM. Okay, you can see that it is of few tons, and then they are using a crane to kind of lift it to put it into the plane. Okay, so this is the hard disk drive. This is such a bulky hard disk drive, you can see. You know how much data it can store? It can store only 5 megabytes. 5 megabytes is just like you can write a leave letter and then store it there. Or you can just store one song. Okay, 5 minutes song you can store in there, that's all. And the cost you can see it is $50,000. Needless to say that how much revolution that has happened in data storage. This is the current hard disk drive that is, we are holding it. Okay, and how much data it can store? Few terabytes, maybe more than 2 terabytes. And how much does it cost? It costs only 4,000 to 5,000 rupees. From $50,000 to less than $100. You see how much difference. And how much density it can store? It can store 1 million times higher than the density that is stored. So we have compacted it to so small, and we are storing lot of data, and then we have come up with a small price. So we should remember that whenever we are making a device, or whenever we are coming up with a new device, or new device architecture or prototype, we should remember 3 things. Okay, it should be compact. It is just like whenever I am buying a phone, what I will see is that whether it can fit in my pocket or not. It should be compact. Second thing, it should be fast. Okay, you know that. I mean, I can't. Whenever I switch on, I should be able to immediately see what I want to see. I cannot wait for a longer time. Third one is it should the power consumption should be small. Power consumption is that battery life should be so high. Okay, so it should not take so much of power. My battery should come for so many days. So we all of us think like that. So whenever I buy a phone, I look for these 3 things. But interesting part is that you should also look for one more thing. It can satisfy that it is compact, it is high speed, low power consumption, but also it should come for a cheaper price. Then only we buy it. Okay, so you need to remember 4 things. So now you can see that compared to 1956, just because of the discovery of GMR phenomena, that is giant magnetoresistance phenomena, the hard disk drive which we got, which is fast, compact, which can store a lot of data at a smaller price. Okay. You may be thinking that when I am telling about we already have a very good hard disk drive, why still we need to do so much of research in spintronics? Of course, I will tell you why do we need to do it. Okay, so with that I will come up with the first topic of my work, that is on the racetrack memory. So this is the current memory architecture. So you take a phone or you take a tab or you take a laptop, right? This is the memory architecture it is there, which is that you have a CPU where all the algorithm and logic units are there, and then this is the processing is happening over there. In CPU, the processing is happening very fast, but you should be able to give the data and then take the data. You give some data, process, you take the data, store it. So the data transfer, right, the speed of the data should be very high. As you can see here, that the speed should be very high. And when you are coming slowly to the bottom, where you have a hard disk drive, the speed of the hard disk drive is limited. You know why? Because whenever you put a hard disk drive, you hear some sound. There is a disk that is rotating. So whenever there is a physical motion that is involved, the speed of the device is going to be small. So when the speed of the device is smaller, you cannot use it directly close to the CPU because CPU works in gigahertz speed. Okay, which is like it can do 10 to the 9 times of processes per computation in 1 second. Whereas hard disk drive, it can do only few hundred megahertz. So you cannot directly use hard disk drive just next to the CPU. People are using static RAM and dynamic RAM close to the CPU. Volatile memory means that both are charge-based devices. So whenever you use a charge-based devices, as I mentioned, there is a lot of standby power that is needed. Which means that, let's say that you turn off your computer, but your RAM is, you need to continuously refresh your RAM. If you don't refresh your RAM, you cannot switch on your computer. You cannot get your Windows on. Okay, same is true for our laptop. Let's say we thought that, okay, I have just shut down my laptop, I left it in a corner and I went for a holiday and came back. After 1 week, the whole charge is over. The reason being is that the RAM is continuously getting refreshed. So even though you're not using your laptop, your memory is getting refreshed and then you're still spending power for it. Okay, that power is called standby power. So why is it happening? Because we are using charge-based devices, which is a volatile memory. What if I can replace this volatile memory, that is the charge-based memory, with a spin-based memory? As I already mentioned, if there is a spin in, let's say, plus y direction, it will always be in plus y direction. If it is a random access memory, you don't need to refresh the memory. It is always there. Unless you change it, it is always there. So this is called non-volatile memory. So when you have a non-volatile memory, there is no standby power. You can save a lot of power. Okay, and it is going to be very energy efficient. Moreover, whenever there is a refreshing, whenever you use your phone for some time, whenever you use your laptop for some time, you know that a lot of heating issues are there. Why there is a heating issues? A lot of power consumption is there. Whenever a lot of power consumption is there, heating is going to happen. That is the reason that every laptop has a fan inside. Every computer has a fan inside. But if at all I use a spintonic based